Good morning. My name is Denis Kouroussis. Today I'll be talking about mitigation of dirty power, as it's called. So before we get into it, let's talk a little bit about what the current state of electrical distribution is from the basics. About 100 years ago, there was a little debate between AC and DC, and we settled on AC because we could actually transform to high voltages very easily using transformers. So we began producing power at 20 kilovolts at some point, and we started transmitting at much higher voltages so we could go long distances. So this is how we won the AC system with our friend Nikola Tesla on the right-hand side of that slide. The basic concept is that when you produce power in a generator, you have an excitation field, you create a magnetic field in the center, and then you have three phases. This is an oversimplified model, of course. And as you spin that magnetic field, you create three phases of voltage, which are purely sinusoidal. So the idea is to keep those phases always coming at the correct frequency and voltage quality. We want to ensure that we have steady voltage levels, whether you're producing at 20 kilovolts on your generation side or you're running 480 volt system. We want to maintain that 480 volts. We want to maintain a low level of transients within the facility. And we want to ensure that interruptions don't happen often, so you're not dropping power. Additionally, we would like to have low harmonic distortion, which usually in today's time is attributed by a lot of VFDs and switching power supplies. And we want to ensure frequency stability and balanced phases. So let's get into it. Why is dirty power or a lack of good power quality a problem? It leads to loss of revenue within your facility. It increases operating costs. If you're in a production facility and you have specific timelines about delivering product, you can miss deadlines. There are safety risks, obviously, and it's additional headaches for staff. A lot of power quality issues are also called within the technician world ghost electrical problems because they can't be diagnosed. And of course, the costs of downtime on some of these manufacturing industries are significant. It's not just about losing a motor that costs $20,000 potentially. It's also about the downtime associated with the loss of manufacturing, which I have some numbers shown here. And for example, in the automotive manufacturing industry, if you lose your production, you're losing $3 million an hour. So why do we have things like voltage instability, and how does it come about? There's usually two culprits. There's utility variation, so something's happening to the utility side, or there's internal facility distribution equipment that has undergone some type of degradation. On the utility side, it's important to remember that utilities have the ability to vary the voltage plus or minus 10%. And that means that if you're specifying equipment within that facility, you should be able to handle some of those transients. And we'll get to that. An example, so I'm Canadian, I'm from Canada. We have a 600 volt system. And a lot of our motors are actually rated at 575 volts because they're widely available. So when the utility starts to ramp up from 600 volts, 610 up to 650, which is, you know, something that they do occasionally, you can start blowing out motors. Additionally, within a particular facility, now you have a distribution system. You have breakers, fuse disconnects, contactors, terminal connections, If any of those things are degrading, i.e. you have loose connections, or you have contactors that have built up a lot of carbon buildup because of arcing, you can get voltage drops and you can get intermittent fluctuations. You can lose power. And of course, if you also have equipment, so a lot of VFDs within a facility, you can create a lot of harmonic distortion. So here's an example of voltage instability within a facility due to a contactor specifically. And you'll notice on the top graph, those voltage transients happen at 6 a.m. in the morning, so we're able to capture that. And as the day progresses with a lot of stop-starts of this particular piece of equipment, by, I think, 10 hours later, we start single phasing. So we're starting to drop a complete voltage channel, and that is leading to single phasing of the motor. This motor did catastrophically fail eventually. Further, this is an example of a voltage transient because of equipment. You'll notice that on the left-hand side of the graph, on the current side, we have a lot of switch mode power supplies happening, and I believe this is from some lighting equipment ultimately. And as we progress, there's a transient that happens because this lighting equipment turns off, and we get a huge spike, a huge spike of current, which also affects the voltage. Now, that may or may not be an issue, but if that starts happening continuously and repetitively at a high frequency, you could damage equipment. Additionally, this is an example of voltage variations over a 7-day trend. So again, this is from Canada. This is from the Toronto region. This is not too bad, but our nominal voltage should be at 600 volts. And you're noticing all the sample points, they're at 595. And at some point during the day, because of loading, so it could be a consequence of loading within the facility itself, as well as utility draw, we're reaching levels of about 583, 580 volts. Not a major problem, but this is an example of the amount of voltage variation. Here's another example of harmonic equipment. Our monitoring equipment is actually deployed on a piece of switchgear, which is feeding about 100 VFDs. Now, the VFDs, the front end of the VFDs are doing some form of power factor correction as they're running, and they're creating this waveform, which is pretty significant. You're seeing peaks of 600 amps. And because of the harmonic distortion in the waveform, we're also slightly distorting the voltage as well. That is not a pure sinusoid anymore. So it's important to understand what is happening at your distribution side in order to maintain good voltage stability. So how do we maintain voltage stability? Because we just talked about it. In my opinion, the first and foremost thing you can do as a starting point is to do some type of very effective monitoring. And I'll give you a little example of a customer site that I was on years ago. There was a 300 horsepower motor, a pumping facility. And under utility power, there was a motor that was running just fine. They had decided to deploy a VFD to run that particular pump. And the VFD would run the pump under utility power. But as soon as they would switch over to backup generation, the utility pump would kick up, the VFD would start running, and eventually after about 20 seconds, it would kick out without ever reaching full speed. So when I got on site, all the electricians were talking about, oh, this is a ghost electrical problem. The generator can't handle this type of load with switching frequency and so forth. And I said, okay, that's great, but do we have any data? So we did some captures, and we noticed doing the captures on startup that sure enough, there was a lot of harmonic distortion because of the VFD. However, if you sat down and did some simple calculations, especially under startup, you would notice that the amount of harmonics on that startup with a VFD were minimal in comparison to what the generator could produce. So it shouldn't be a problem theoretically. So we did some startups, we did some captures, and what we noticed was on the startup, there were significant voltage fluctuations that the generator was ultimately producing. And because of the voltage fluctuations, the VFD was going into under voltage protection and kicking out. So we did some more testing, and it turns out that the sense circuit of the voltage regulator for the generator was accumulating sense error and was effectively turning off the voltage regulation, the field current for the generator. So we were able to solve that problem by a simple $200 isolation transformer and maintain constant voltage, and the VFD started running up. Now, the reason I tell this story is because I was called in by the director of maintenance for this particular facility, and his concern was that the electrical contractor that deployed the VFD had come back and wanted to sell a big power filter for $200,000 to them to fix the problem without any guarantees. So if you have data, you can potentially save a lot of money. Furthermore, on the voltage stability within a facility, you can ensure, so once you have data, you can ensure that your transformer voltage taps are set accordingly to maintain the proper voltage levels. Additionally, on the predictive maintenance side, you can do some level of thermal imaging on your distribution equipment. So this will isolate hotspots. And then you can add harmonic filters on VFDs, active filters, and ultimately, if you're really concerned about voltage variations, a UPS, which is very expensive. Frequency shifts. This is something that usually comes directly from the utility and not much you can do in the way of within a facility, so you can't affect frequency. The frequency shifts happen because of generation imbalance. So if your utility is loading up one phase significantly to the point of overload on that generation side, you will get a frequency shift. Load imbalance, faults and disturbances, anytime you have a short circuit condition within a utility, you will pull down a large amount of current, and that will slow down your ultimate system. And then we have renewable energy sources, which are injecting a lot of harmonics into your utility, which can also drag down on the governance circuits of your generators. And there's resonance as well as islanding. So if you take a section of the grid off, the rest of it, the remaining generators within that island may not be able to carry the full load. So the only way to get around this really, if you're experiencing a lot of it within a facility, for example, is to really go down the path of a UPS. And then balancing of your phases, that's something that you have to do at the utility level. So houses, for example, will always use one phase rather than all three phases. So you got to balance out entire neighborhoods, for example. And similarly, you need to do the same thing within a facility, right? So you want to be able to ensure that there's not a lot of single phase loads spread out, pulling down one side of your distribution system. So here we're going to do a plug for our product. So the captures that we showed were actually captured with the system. We have a small VI module, which is calibrated to the CTs that we're going to be measuring current with. And then we need some voltage tabs. The node on the left-hand side here is our data acquisition device. This reports into the cloud, and it is programmable remotely to be able to capture everything power quality-wise, transient-wise, and so forth. We have our own proprietary algorithms in the back end. We call it InsiteAI for fault detection. If we see something anomalous within a system, we will alert our customers and ourselves. And one of the key advantages of having this system cloud-based is that we get data integrity. So all the data gets lifted up into the cloud, and we have it there. And we're able to connect to our actual nodes, update firmware, as well as thresholds to be able to catch those critical ghost electrical problems. And lastly, we provide engineering support. So we're there with our customers to give them everything they need and understand what the waveforms are telling us. I'm fast today. So to conclude, dirty power can cause a lot of havoc within a facility, and this can cost a tremendous amount of money in terms of equipment and downtime. So it's critical to be able to monitor and correct the situation. And I think monitoring is the first most important step in actually building up some type of power quality strategy.